Is it working? Okay. Okay. So thank you. And I'll present my work, Effectful lenses, there and back with different monads. So let's start by considering a motivating example. We know that lambda expressions can be encoded in either using variable names or using the de Bruijn indices. So these two representations are equivalent to each other, and you can convert between them freely. So here we consider this challenge to design a bidirectional converter between the two representations. So if we are converting from the left to the right, that's the usual algorithm apply, and you can just do it the usual way. But if we consider the conversion from the right to the left, that is from the nameless representation to the named representation, then we have a problem because there are actually infinitely many different names you can use for the binders due to alpha equivalence. So the challenge here is to recover the names exactly as they were when we are converting from the right to the left. So as it turns out, it seems very obvious that it should be a use case for bidirectional transformations, or lenses as we know it. So we have two different data structures, one called the source and the other called the view. And we are doing synchronization between the two. So here the source is named and the view is the nameless. So there's this forward transformation called get, converting from the source to the view. And after we get the view, we can apply some addeds to it, and we can try to convert it back. But as we have already discovered, this conversion does not work because there is not enough information for this conversion back. So instead, alongside the modified view, we also take the original source. So when we combine the two pieces of information together, we can get an updated source. And the conversion back is called the put component. And get and put together form a lens. So is the problem solved? No, actually. Because in this specific challenge, there are some monadic effects required in the conversion process. So for example, consider this pair, this F binding, this F use side, and the index 2. F corresponds to the index 2 because we know that F was bound outside here. So in order to use this information, we need to maintain a context, which requires using the reader effect. And let's also consider this example where I use this unbound variable y. So we cannot directly convert this to the right-hand side because we cannot determine a proper index for y. So in this case, we want to report a failure, which requires using the array effect. And finally, let's consider if we start with a nameless on the right, and we directly convert back to the left, which means the names are unspecified. And we might want to ask the user for the names. And if we want to do that, we need to interact with the user, which requires using the I/O effect. So these are all the potential effects we want to use for this conversion process. And it turns out that the traditional lens framework does not support monadic effects. So the problem is to combine lens frameworks with monadic effects. So there are some very useful properties comes with lens frameworks. Like we have a correctness specification for lenses, such that we have exact recovery when we are converting from the view to the source. And we also have consistency between the two directions of the conversions. And the lens framework also supports compositional programming, which means we can combine smaller programs into larger programs using various combinators. And we want to maintain these two strengths for the lens frameworks, but introducing the effects into the picture, which we want to use, for example, these three effects. So let's first consider the two strengths for pure lenses. We have this correctness specification, which we call the round-trip properties. They specify the correctness or consistency between the two directions of the conversion. So the get-put property states that if we get, and we get the view, and we do not modify it, and we directly put it back, we should get back the exact same source, which means exact recovery. That's our requirement previously. And the other way around, if we first put and then we get, we should get back the view we just put in. So that it means all the information in the view should be reflected in the source. And this entails the consistency between the two conversions. And for compositional programming, one very important thing about lenses is that they can be composed, which means we can chain lenses into a pipeline. So if we have a lens f between x and y, and we also have a lens between y and z, then we can form this lens g after f, which is between x and z. The important thing about this composition is that it preserves the round-trip properties, and this is key to compositional programming. So if we look at the previous works, we see this is a known problem when we combine lenses with monads. So you might just think that we can just do it by introducing the monad M into the two return values, the return types of get and put, and we get this naive encoding. And then we discover that when we try to define a composition, it becomes very problematic. We can still define it by directly generalizing from the pure definition for lenses, and we get this definition. But when we consider their composition, for example here, first get followed by put, and we expand the definition for get and put respectively. So if we want to show that composition preserves the round-trip properties, the goal is to show that the get-put of this composition follows from the get-put property for both f and g, which means we want to find a substructure for get-f followed by put-f in this composition chain. And if we look at the right-hand side, we see this structure where we have this extra get-g in between. So it means that we cannot actually apply the get-put of f to simplify this expression. And all the reasoning are stuck, and we are out of luck. So in the previous works, it is decided that the problem is that get is impure. So they make get pure by removing the monad M from get. And in this case, if get is pure, then due to referential transparency, we can just show that composition really preserves the round-trip properties. But that does not apply to our motivating example because we really want to use effects in both of our directions. So the first question is, can we allow impure get? Okay. And the second question comes from the semantics for the round-trip properties. So if we directly generalize the get-put property from pure lenses, we specify that this in terms of get followed by put is equal to pure. Then on the left-hand side, get performs some effect here. But if we consider right-hand side, there's no effect in the round trip, which means the effect of get is somehow canceled by put. And recall that we want to use effects like error and IO, and they cannot be meaningfully canceled. So our second question is, how do we support non-cancelable effects? And finally, recall that we want to use IO to interact with the user input. But on the other hand, get does not have access to IO. So we should be able to use different monads in get and put. And the question is how? So when we really use different monads in get and put, we see that the monadic length composition itself becomes invalid because the definition previously shown uses get input, and it becomes invalid because those are using different monads. And also, we need to find out a way to describe the interactions between the two effectful computations, which use different monads. So the plan for the rest of the talk is to address these questions. And as it turns out, the definition for lens are key to solving questions 1 and 3, and the round-trip properties are there to solve the last two questions. So first, we consider a definition. We discovered that we can solve the questions by migrating from the previously shown encoding for lenses to this well-known representation of lenses called lenses with complements. and they are known to be equivalent to each other. So still we have the source and the view. We can convert from the original source to the extracted view by using GAT. And then this conversion discards some information, so we cannot directly put it back. But instead of taking the original view, we require that the forward direction computes something called a complement alongside the view. So the complement saves the lost information in the forward transformation. And then in the backward direction, we can combine this complement with the modified view to get back the updated source. By using this structure for lenses, we see that in the definition for the composition, the two directions get and put are cleanly separated. So question 1 and question 3 are addressed. Now we can consider this definition. This is definition for pure lenses with complements. We just add the two monads M and N to lenses with the complements. And we define the composition by directly generalizing the pure definitions. And then we consider the round-trip properties, which are the correctness specification for lenses. We see that the round-trip properties for pure lenses are actually specified using function inverse. So we generalize invertibility relation to what we call the round-trip relations. We have this relation R between the two Kleist arrows to describe something which is a generalization of F after G is ID. And based on this round-trip relations, we add the extra logic to handle the complements, and we get the round-trip properties for lenses. And it can be specified using a pair of round-trip relations because we have two different round-trip properties. And then the other two questions are addressed. So based on these definitions, we can start to build a rich combinator language for the user to construct useful programs in our framework. And as it turns out, the monads M and N and the round-trip relations, they are specified by the user. But we want a general theory that can be used for whatever effects the user might choose. So for example, we want some combinators like ID and composition, which provide a category structure for lenses. And also we want product and sum, which supports polynomial functors. And finally, we want something to support manipulating the complements for the lenses. And all of these combinators should work regardless of what effects the user might choose. So our solution is to specify a set of axioms, these 5 axioms, to bridge between the two lens. So as long as the round-trip relations the user specified satisfy these 5 axioms, all of our combinators would work. And now let's get back to the motivating example and see how we solve it. So an important lesson is that program structure should follow data structure, right? So we first consider the data structure to be synchronized, which is the expression here. As we can see, it is a recursive data type. So the first thing we can do is to apply some recursion scheme to reduce it to a polynomial functor. And the polynomial functor has a sum of product structure. So we can first use some combinators for sum, which breaks down into 3 different branches. And then for each branch, it is a product structure. So we can use the product combinators. So here's the actual code for the example. First, we choose a monad to describe the effects used in the example. Here, I combine the reader and the error here. And we also choose the round-trip relation for this monad M. And here we see the top-level converter is converting between the named and nameless expressions. And we use the recursion scheme here, so we get the algebra for the recursive conversion. And then we consider the algebra. As I have just said, it's in the product of sum, sum of product structure. So we apply sums here to reduce it to 3 branches. And for each branch, we can define the lenses. So we can use other combinators in constructing these different branches. So to conclude, we present the first lens framework with different effects in get and put. And it is based on the alternative encoding for lenses, which is called lenses with complements. And we propose using round-trip relations to describe the interaction between the two different effects. And the round-trip properties are then built on top of the round-trip relations by adding the extra logic for complements. And the framework supports compositional programming by saying that all of our combinators preserve the round-trip properties. And finally, we have this case study. So there are actually 3 different flavors for this converter in the paper. So if you are interested, you can check it out. And the last thing I want to say is that all of our theory and the examples are implemented and verified in AGDA. So that's all of my presentation. Thank you.
So I had a question already. Maybe if you could say a bit more about these round-trip relation. Can you show an example of what that looks like? Or?
Oh, right. Okay. So there are some examples in the paper, but I can briefly describe how it works for effects like reader or error. So if we consider reader, what we want is that the same context is used for both directions. So the actual definition is that we run the reader, we interpret the reader effect by supplying the same context S to both directions. And then we either use another relation for the base monads, or we just directly for identities. Then, sorry, it might be too complicated. Let's just consider the array effect. So it basically says if the forward succeeds, then the backward should succeed, and it returns the same value. So it's like the forward should be OK, and then backward should also be OK, and it should return the input value x, which should be the same as the original input. So it's really that for each effect we want to use, we specify several different potential round-trip relations to describe the semantics you want. Yeah. I don't know if it answers the question.
User chosen.
Right, it's specified by the user.
Okay.
Very intriguing work. I'm just trying to understand your response to question 2 about supporting non-cancellable effects.
Okay.
As I understand it, your contribution is that you have reduced it to a law that if you've got non-cancellable effects, they have to satisfy. Is that correct?
So the way that we support non-cancellable effects is to delegate the responsibility to the user, right? Because if the user want non-cancellable effects, they can describe what they want with these effects by specifying these round-trip relations. So okay. This relation captures how the effects should interact with each other.
Right. Have you looked, instead of, like, it's a related question, like, for instance, what monads support cancellable effects, right? Like, for instance, now you have given an example of logging as an example of a non-cancellable effect, but the logging, or the so-called writer monad, if it was not just if it were not just a monoid, but in fact it was a group, then you could basically append a negative log to cancel the stuff in the log, you see. So have you looked at monads that are cancelable?
So I guess, yes, there might be some monads that can be canceled. But the point is that we want a framework that extends to both things, right? It doesn't only support non-cancelable effects. It also supports other cancelable effects. So in fact, if your effect is cancelable, you just like, for example, if the get and put are using the same monad, you can just use a class decomposition to compose them, and your round-trip relation would be very easy to specify that RFG is just that F classically fish G is equal to pure, and that's the way you specify the round-trip relation for cancelable effects.
Something else I was wondering about, have you looked at other prisms? So, for example, these lenses that sort of give you a view on multiple copies of the same structure? Or?
Right. So all the other, like the optics or the prism, the traversals, and all the other in the hierarchy, I think there might be some incompatibilities between the two because the fundamental encodings are relatively different. We haven't really looked into all the other variants in the optic hierarchy, but it might be an interesting thing to look in the next step. Yeah.
Okay. Last chance.